Picture a moment when everything, every galaxy, every star, even the atoms in your body, was compressed into a space smaller than a single grain of sand. A moment so unimaginably hot and dense that light itself couldn't escape. This wasn't just the beginning of our universe, it was the birth of reality as we know it. The Big Bang wasn't an explosion in space, it was the explosion of space, a fiery eruption of energy and matter that set the stage for everything to come. And in those first fleeting instants, the universe was a seething cauldron of chaos, where the rules of physics, as we understand them, hadn't even begun to take shape. What did that primordial universe look like? How did it transform from a raging inferno into the vast, structured cosmos we see today? The answers lie in those first critical moments, and they hold the key to understanding not just where we came from, but what the universe itself is made of. Think about this. In the first fraction of a second after the Big Bang, the entire universe was hotter than the core of the Sun, a swirling soup of particles moving at nearly the speed of light. There were no stars, no planets, not even atoms, just raw energy and the building blocks of matter colliding in a cosmic dance. And yet, within that chaos, the seeds of everything we see around us were being planted. The forces that govern our universe, gravity, electromagnetism, the strong and weak nuclear forces, were emerging from the frenzy, carving order out of the storm. It's like watching the first strokes of a painter's brush on a blank canvas, the moment when the universe began to sketch its own masterpiece. But how did it happen? What were the conditions that allowed this incredible transformation to unfold? This is the story of the universe's first chapter, a tale written in the language of physics and etched into the fabric of space itself. It's a story that connects us all because every atom in your body, every speck of dust in the cosmos, traces its lineage back to those fiery beginnings. By peering into those early moments, we're not just uncovering the past, we're unlocking the secrets of how galaxies form, how stars ignite, and how the very building blocks of life came to be. So join me as we travel back to the dawn of time, to a universe so alien and yet so familiar, where the impossible became inevitable. The journey starts now, and trust me, you won't want to miss what comes next. To even begin wrapping our minds around the Planck epoch, we have to think smaller than small. This was a period so brief that the number describing it has 43 zeros after the decimal point. Imagine trying to capture the blink of an eye, then dividing that moment into a trillion pieces, and then doing it again and again until the slice of time becomes almost meaningless. That's the scale we're dealing with here. In that first incomprehensible flicker, the universe was so dense and energetic that the very concepts of here and now didn't apply the way we understand them today. Space and time were tangled together in a seething quantum foam, where particles flickered in and out of existence faster than reality could keep up. What's even more astonishing is that our trusted laws of physics simply don't work here. Einstein's theory of relativity, which explains the cosmos on grand scales, and quantum mechanics, which governs the tiny world of particles, completely break down when pushed into these extreme conditions. It's like trying to use a weather forecast to predict the path of a single raindrop in a hurricane. The tools we have just aren't built for this. Scientists suspect that during this fleeting moment, gravity, the force that shapes galaxies and bends light, split away from the other fundamental forces, setting the stage for the universe to evolve. But how? That's where the mystery deepens. Some theories suggest that quantum fluctuations, those tiny random jitters at the subatomic level, might have been the universe's first brushstrokes. These microscopic ripples in the fabric of reality could have been stretched by the rapid expansion of space itself, eventually growing into the vast cosmic web of galaxies we see today. It's as if the universe rolled a pair of dice in those first moments, and the outcome determined everything that followed. Yet without a working theory of quantum gravity, a way to reconcile the immense and the infinitesimal, we're left peering into the darkness, catching only glimpses of what might have been. The Planck epoch remains the ultimate frontier of cosmology, a realm where the answers could rewrite not just our understanding of the universe's birth, but the very nature of reality itself. As the universe expanded beyond the Planck epoch, temperatures began to drop, though cool is a relative term when we're still talking about a quadrillion degrees. This was the grand unification era, a fleeting moment when three of nature's fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been indistinguishable, merged into a single, unified superforce. Picture the universe as a simmering pot of cosmic soup where the ingredients haven't yet separated, all swirling together as one. For a sliver of time around 10 to the negative 36 seconds after the Big Bang, the laws governing particle interactions were simpler, more symmetrical. What's truly mind-bending is that during this era, matter and antimatter were in perfect balance, constantly popping into existence as particle-antiparticle pairs before annihilating each other in bursts of pure energy. Under these extreme conditions, exotic particles we've never observed, like magnetic monopoles, theoretical entities carrying a single magnetic charge, might have briefly flourished. These could be relics of that unified force, frozen remnants of a time when the universe operated under different rules. Some theories suggest these monopoles should still exist today, lurking in the cosmic background like fossils from the universe's infancy, though none have been detected yet. The end of this era was marked by a dramatic phase transition, like water freezing into ice but on a cosmic scale. As the universe cooled further, the superforce broke, splitting into the distinct forces we recognize today. This sudden shift released an enormous amount of energy, potentially driving an exponential expansion known as inflation, a growth spurt so violent it stretched the universe from subatomic size to something approaching a grapefruit in less than a blink. But here's the puzzle. When matter and antimatter annihilated during this era, they should have cancelled each other out completely, leaving behind a universe filled with nothing but light. Yet somehow, for every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny imbalance is why stars, planets, and we exist at all. Unraveling the grand unification era isn't just about peering into the past, it's about decoding the universe's hidden blueprint. The forces that emerged from this phase govern everything from the stability of atoms to the nuclear reactions powering stars. If we can reconstruct how symmetry broke in those first moments, we might finally understand why matter won out over antimatter, solving one of cosmology's greatest mysteries. The answers could be written in the faintest signals from the early universe, waiting for us to listen. If you've ever blown up a balloon, you've seen how its surface stretches. Tiny dots drawn on the rubber suddenly spread apart, becoming larger and more distant. Now imagine that balloon expanding faster than the speed of light, doubling in size every fraction of a second until it's billions of times bigger than when you started. That's cosmic inflation, the universe's most dramatic growth spurt. Around 10 to the negative 36 seconds after the Big Bang, space itself began stretching at an unimaginable rate, inflating from smaller than a proton to something trillions of times larger in less than the blink of an eye. This wasn't just rapid expansion, it was exponential, like a snowball rolling downhill that somehow turns into an avalanche mid-flight. What's remarkable isn't just the scale of inflation but the problems it solves. Before this theory, scientists struggled to explain why the universe looks so similar in every direction, why the temperature of the cosmic microwave background, the afterglow of the Big Bang, varies by less than 1 part in 100,000. Without inflation, regions of space too far apart to ever exchange heat or information somehow reached equilibrium, like 2 cups of coffee placed on opposite sides of the Earth, mysteriously cooling to the exact same temperature. Inflation fixed this by stretching a tiny, uniform patch of the early universe to cosmic proportions, smoothing out irregularities in the process. But inflation did something even more profound. It turned quantum noise into cosmic architecture. Microscopic fluctuations in the primordial soup, random ripples no bigger than a billionth of a billionth of a billionth of a meter, were stretched to astronomical scales during inflation. These tiny wrinkles became the seeds for all future structure, the denser regions where galaxies would eventually cluster, the slight overdensities that gravity would later sculpt into stars and planets. Without these imperfections, the universe might have remained a featureless void, too smooth for anything interesting to form. The aftermath of inflation was just as spectacular. When this runaway expansion finally ended, the energy driving it had to go somewhere, and it flooded the universe in a fiery cascade of particles and radiation, reheating the cosmos to temperatures near 1 trillion degrees. This was the Big Bang in the truest sense, the moment when the universe as we know it truly began. Inflation didn't just shape space, it set the clockwork in motion for everything that followed, from the first atoms to the largest galaxy superclusters. Yet mysteries remain. What triggered inflation in the first place? What made it stop? Some theories suggest it wasn't a one-time event but part of a grander cycle, with other universes inflating beyond our own. Others propose that inflation's fingerprints might still be detectable in gravitational waves echoing through the cosmos. One thing's certain, this fleeting moment of hypergrowth didn't just solve old puzzles, it opened new ones, reminding us that the universe's earliest chapters are still being decoded. As the universe cooled from its inflationary frenzy, it entered a phase so extreme that even protons and neutrons couldn't hold themselves together. This was the Quark Epoch, a time when the building blocks of matter roamed freely, unshackled by the forces that would later bind them. Picture a cosmic mosh pit, where quarks, the fundamental particles that make up protons and neutrons, zipped around at nearly the speed of light, colliding and rebounding in a frenzy of pure energy. Gluons, the sticky particles that normally glue quarks together, were overwhelmed by the heat, leaving quarks to bounce around like marbles in a superheated blender. What made this era so bizarre was the sheer density of the universe. Temperatures soared above 1 trillion degrees, creating conditions so intense that matter and antimatter particles constantly materialized from the energy of collisions, only to annihilate each other microseconds later in bursts of light. It was a relentless cycle of creation and destruction, like a cosmic game of whack-a-mole where particles appeared and vanished faster than the universe could keep track. But here's the twist: for every billion matter-antimatter annihilations, one extra quark survived. That 1 in a billion imbalance might seem insignificant, but it's the reason galaxies, planets, and even we exist today. Without that tiny surplus, the universe would have been left with nothing but empty space and radiation. The Quark Epoch lasted just a few microseconds, but it set the stage for everything to come. As the universe continued expanding, temperatures finally dropped enough for quarks to start feeling the pull of the strong nuclear force, the same force that holds atomic nuclei together. Gluons began doing their job, corralling quarks into groups of 3, forming the first protons and neutrons. It's like watching a chaotic crowd suddenly organize into teams, each group finding its place in the grand scheme of things. But before that could happen, the universe had to endure one last cosmic trial, a phase transition so violent it reshaped the very fabric of reality. This fleeting moment holds clues to one of physics' greatest mysteries. Why is there something instead of nothing? The Quark epoch wasn't just a chaotic interlude, it was the universe's first experiment in asymmetry, a delicate imbalance that tipped the scales in favor of matter. Scientists still don't fully understand why matter won out, but hidden in the behavior of those early quarks might lie the answer to why we're here at all. The Quark epoch may have been brief, but its legacy is written into every atom in your body, a reminder that the universe's most pivotal moments often happen in the blink of an eye. The universe was still a seething, chaotic battlefield, but now the rules of engagement were changing. As temperatures dipped below 10 trillion degrees, quarks could finally stick together long enough to form hadrons, the family of particles that includes protons and neutrons. Imagine trying to assemble a delicate house of cards in the middle of a hurricane. That's what it was like for these fundamental particles trying to bind in the midst of such unimaginable energy. Gluons, the force-carrying particles that act like cosmic glue, began overcoming the chaos, pulling quarks into stable groups of three. Protons, with their 2 up quarks and 1 down quark, and neutrons, with 1 up and 2 down, became the universe's first durable building blocks. But survival wasn't guaranteed. Particle collisions remained so violent that many of these newborn hadrons were torn apart almost instantly, their quarks scattered back into the primordial soup. It was a cosmic game of tug-of-war, binding energy versus thermal chaos with the universe itself as the referee. Meanwhile, matter and antimatter were still locked in their final, devastating showdown. For every proton that formed, an antiproton emerged, and their collisions lit up the universe in flashes of annihilation. Most of these pairs wiped each other out, converting their mass back into pure energy. Yet somehow, against all odds, a tiny fraction of matter survived, just 1 proton for every billion that vanished. That razor-thin margin is the reason anything exists at all. The balance between protons and neutrons was another delicate dance dictated by the cooling universe. At these temperatures, the weak nuclear force could still transform protons into neutrons and vice versa, like a cosmic alchemist reshaping matter on a whim. But as the universe expanded, this process began to favor protons. Their slightly lower mass made them easier to produce. By the time the Hadron epoch ended, roughly 1 neutron remained for every 7 protons, a ratio that would shape the chemistry of the future cosmos. This imbalance determined how many heavy elements could form later, setting the stage for the diversity of atoms we see today. Hidden in this turbulent era are clues to one of physics' biggest puzzles. Why does the universe prefer matter over antimatter? The slight asymmetry that spared those 1 in a billion protons hints at undiscovered laws of nature, perhaps new particles or forces that tip the scales in matter's favor. Experiments like those at the Large Hadron Collider are recreating these extreme conditions, searching for the subtle cracks in nature's symmetry that made our existence possible. The Hadron epoch wasn't just a transition, it was a cosmic bottleneck, a moment when the universe could have ended up empty but didn't, and the particles that made it through became the raw material for everything that followed: stars, planets, and life itself. As the universe continued its relentless expansion, temperatures finally dropped low enough for a new cast of particles to take center stage: the leptons. Electrons, the lightweight, negatively charged particles that would one day orbit atomic nuclei, now outnumbered their heavier counterparts, but this was no calm transition. The cosmos remained a churning plasma, so energetic that electrons couldn't yet settle down with protons. Instead, They zipped through space like hyperactive fireflies, constantly colliding with photons in a frenetic dance that kept the universe opaque, a glowing fog of charged particles and light. Neutrinos, the ghostly, almost massless particles that barely interact with matter, played a crucial role in this era. Born in the fiery collisions of the Quark and Hadron epochs, they suddenly found themselves liberated as the universe thinned out. No longer trapped in the cosmic plasma, they began streaming freely in all directions, carrying away energy like silent witnesses to the chaos they left behind. Billions of these primordial neutrinos pass through your body every second, remnants of this ancient epoch, yet they slip through unnoticed, their secrets intact. Somewhere out there, these elusive particles might still hold clues to the universe's earliest moments, if only we could catch them. What's remarkable about the lepton epoch is how delicately balanced it was. Electrons and their antimatter counterparts, positrons, were locked in the same deadly dance as earlier particles, constantly annihilating each other, only to be recreated by the intense radiation bathing the universe. But as temperatures kept falling, the energy of photons dropped below the threshold needed to spawn new electron-positron pairs. The scales tipped decisively, annihilation won out over creation. In a final, dramatic purge, nearly all the positrons vanished, leaving behind just enough electrons to one day balance the positive charge of all those surviving protons. This era also set the stage for one of the universe's most pivotal moments, the formation of the first atoms. But that wouldn't happen until temperatures cooled further, allowing electrons to finally be captured by atomic nuclei. For now, the universe remained a seething, ionized soup, its fate hanging in the balance. The lepton epoch might not have the explosive drama of inflation or the Quark-Hadron transition, but it was a quiet revolution, the moment when the universe shed its earliest, most chaotic layers and began inching toward structure. And those relic neutrinos, they're still out there, whispering the story of a time when light couldn't travel freely, and the cosmos was learning how to become transparent. For thousands of years after the lepton epoch, the universe was a blistering sea of light, not the gentle glow of stars, but a blinding radiation so intense it could tear atoms apart before they even formed. Photons, those fundamental particles of light, weren't just passing through space. They were space, carrying so much energy that they dictated the universe's very structure. Matter didn't stand a chance. Electrons, freshly liberated from their antimatter annihilation, were sent ricocheting like pinballs through this photon storm, too energetic to settle into orbits around atomic nuclei. The cosmos was a fog of charged particles, a plasma so dense that light couldn't travel more than a fraction of an inch before being absorbed and re-emitted, trapping the universe in a glowing, opaque haze. This photon-dominated era was more than just a cosmic traffic jam. It was a crucible shaping the future of everything. The relentless pressure of radiation acted like an invisible hand, smoothing out tiny lumps in the primordial soup, ironing wrinkles from the fabric of space itself. Those subtle density variations, the ones inflation had stretched across the cosmos, were now being sculpted further, their contours refined by the constant push and pull of light. It's like blowing on the surface of a cup of coffee. The swirling liquid evens out, but beneath that smoothness, hidden currents still linger. These nearly imperceptible ripples would one day become the seeds of galaxies, but for now they lay dormant, waiting for their moment. Meanwhile, photons weren't just shaping matter, they were outweighing it. In terms of raw energy, light particles held the upper hand, their collective brilliance dwarfing the mass of all the protons and electrons combined. This imbalance meant the universe's expansion wasn't just driven by the momentum of the Big Bang. It was turbocharged by radiation's relentless pressure, like a sailboat catching a cosmic wind. Yet even as photons ruled supreme, their reign was destined to end. With every passing millennium, the universe stretched a little further, its contents diluting, its energy bleeding into the void. Temperatures continued their inexorable slide, dropping from millions of degrees to mere thousands. And then, almost imperceptibly at first, the balance of power began to shift. The stage was set for one of the cosmos' most dramatic transformations, the moment when light would finally loosen its grip, allowing matter to take center stage. But before that could happen, the universe had to endure one last fiery act, the release of the cosmic microwave background, a snapshot of this searing epoch frozen in time. The photons that once ruled the cosmos wouldn't vanish, they'd simply fade into the background, their story etched into the sky in faint microwaves, waiting for us to decode their secrets billions of years later. This wasn't just the end of an era, it was the beginning of clarity, the moment the universe finally became transparent to its own light. 3 minutes after the Big Bang, the universe had cooled just enough for something extraordinary to happen. The first atomic nuclei began to form. This wasn't just any chemical reaction. It was the birth of the very elements that would one day become the building blocks of stars, planets, and life itself. Protons and neutrons, freshly minted from the chaos of earlier epochs, finally had a chance to stick together through the strong nuclear force, the same glue that holds atoms together today. But this wasn't a leisurely process, it was a race against time, with the universe expanding so rapidly that this window of opportunity lasted barely 17 minutes. Imagine trying to bake a cake in an oven that's cooling by the second, where the ingredients only work within an exact temperature range. That's what nucleosynthesis was like, a delicate balancing act between the universe's falling temperature and the frantic collisions of particles. At first, single protons grabbed single neutrons, forming deuterium, the heavy isotope of hydrogen. But deuterium is fragile, easily torn apart by the still intense radiation bathing the cosmos. Only when temperatures dipped below 1 billion degrees could these deuterium nuclei survive long enough to fuse further, capturing additional protons and neutrons to form helium. What's astonishing is how precise this nuclear recipe turned out to be. For every 16 protons that became hydrogen nuclei, about 4 combined into helium, a ratio that would shape the future chemistry of the entire cosmos. Trace amounts of lithium and beryllium also emerged, but heavier elements like carbon or oxygen couldn't form yet. The universe was simply too young and too sparse. Those would have to wait for the furnaces of stars billions of years later. This primordial mix, roughly 75% hydrogen, 25% helium, and a whisper of lithium, became one of the strongest pieces of evidence for the Big Bang theory. When astronomers measured the abundances of these elements in ancient gas clouds, they matched the predictions almost perfectly. But here's the twist: this brief nuclear alchemy almost didn't happen. If the strong nuclear force had been just a fraction weaker, protons and neutrons might never have bonded, leaving the universe as a thin soup of free particles. If gravity had been stronger, the cosmos might have collapsed back on itself before nucleosynthesis could begin. Instead, those 17 minutes set the stage for everything to come. The first stars would ignite using this hydrogen fuel, forging heavier elements in their cores, while helium would become the ash that powered stellar evolution. Without this fleeting moment of fusion, the periodic table might have remained nearly empty, and the universe as we know it would never have taken shape. Hidden in these elemental ratios are clues to the universe's deepest mysteries. The exact amount of deuterium, for instance, tells us how densely packed protons and neutrons were during those critical minutes, offering a snapshot of the cosmos at 3 minutes old. Even today, the echoes of nucleosynthesis linger in every atom in your body, the hydrogen in your water, the helium in party balloons, all relics of that explosive beginning. It's a reminder that the universe wasn't just born in an instant, it was forged, element by element, in a fire that burned bright and fast, leaving behind the raw materials for all that would follow. After the fireworks of nucleosynthesis faded, the universe plunged into its longest night, a profound darkness stretching across hundreds of millions of years. This wasn't just an absence of stars, it was a cosmic void where light itself was imprisoned. The once scorching plasma had cooled enough for electrons to finally settle into orbit around protons, forming neutral hydrogen atoms. But this newfound stability came at a cost. Without free electrons to scatter photons, light could now travel freely, only there was almost nothing left to emit it. The universe became a vast, unlit expanse, a fog of hydrogen so thick it swallowed any stray radiation whole. Yet beneath this stillness, imperceptible changes were unfolding. Those microscopic density variations imprinted during inflation, the ones radiation had smoothed but not erased, were now under gravity's spell. Like invisible hands gathering dust, gravity pulled ever so slightly harder on the denser patches, coaxing hydrogen atoms closer together. Millimeter by millimeter, light year by light year, matter began to clump around these cosmic blueprints. The process was agonizingly slow, a whisper against the roar of the early universe's violence, but relentless. What started as fluctuations smaller than a proton would one day become galaxies. The darkness wasn't uniform. In the coldest, densest regions, hydrogen molecules formed, their faint vibrations bleeding away precious heat and accelerating collapse. Elsewhere, the ghostly pull of dark matter, still mysterious today, worked behind the scenes, its gravity knitting together structures no ordinary gas could sustain. And all the while, the universe kept expanding, stretching wavelengths of the surviving radiation into ever deeper reds, a silent testimony to time's passage. Then, in pockets where gravity won its tug of war with cosmic expansion, something miraculous happened. Hydrogen clouds collapsed until their cores ignited under unimaginable pressure, triggering nuclear fusion. The first stars burst to life, not with the gentle glow of modern suns, but as behemoths hundreds of times more massive, burning furiously blue and dying young in spectacular supernova. Their ultraviolet radiation ripped through surrounding hydrogen, reionizing atoms and flooding the cosmos with light once more. The dark ages were over, but their legacy shaped everything. Those first stars forged the heavy elements that would seed future generations of stars, planets, and life. Their light, stretched by billions of years of expansion, still reaches us today as a faint whisper in radio telescopes, the signature of hydrogen waking from its slumber, the dawn of a universe no longer alone in the dark. Around 380,000 years after the Big Bang, the universe finally caught its breath. The temperature had cooled to roughly 3,000 degrees, still hotter than molten lava, but now just cool enough for electrons to surrender their frenetic dance and settle into orbit around atomic nuclei. This moment, known as recombination, wasn't just a quiet chemical shift, it was the universe's first true clarity. For the first time, photons, those particles of light that had been trapped in a relentless game of cosmic ping-pong with free electrons, could travel unimpeded across space. The universe, once a glowing fog, became transparent, like a curtain lifting to reveal the stage of the cosmos. The aftermath of this transformation is still visible today as the cosmic microwave background, a faint glow that permeates every corner of the sky. It's often called the afterglow of the Big Bang, but it's more than just a relic, it's a fossilized imprint of the universe's infancy. The CMB captures the universe at that critical moment, its slight temperature variations, fluctuations of just one part in 100,000, revealing where matter was slightly denser or sparser. These tiny ripples were the seeds of all future structure, the blueprints from which galaxies and galaxy clusters would eventually grow. What's astonishing is how perfectly this snapshot aligns with our theories. The patterns in the CMB match predictions made about the early universe's composition, confirming that ordinary matter makes up only about 5% of the cosmos, with dark matter and dark energy accounting for the rest. The CMB is also eerily uniform, a testament to inflation's smoothing effect, yet those minuscule imperfections tell a deeper story. They're the fingerprints of quantum fluctuations from the universe's first moments, stretched to cosmic proportions and frozen in time. But recombination didn't just free light, it also altered the universe's very structure. With electrons now bound into atoms, the cosmic plasma vanished, and gravity could finally get to work without the disruptive pressure of radiation. Those denser regions in the CMB became gravity's footholds, slowly pulling in more and more matter over millions of years. The universe was no longer a featureless soup. It was a canvas with the faintest brushstrokes, waiting for time and gravity to fill in the details. This moment also marked a profound shift in how the universe communicated with itself. Before recombination, particles interacted constantly, a chaotic soup where energy was shared and redistributed in a flash. Afterward, the cosmos became eerily quiet, with atoms drifting apart in the expanding darkness. The CMB is the last collective message from that early era, a whisper from a time when the universe was 1,000 times smaller than it is today. And thanks to satellites like Planck and WMAP, we've decoded that whisper, uncovering secrets about the universe's age, shape, and ultimate fate. Yet for all we've learned, the CMB still holds mysteries. Why are certain large-scale patterns in the radiation unexpectedly faint? Could there be signs of other universes imprinted at the edges of our observable cosmos? Every new observation peels back another layer, reminding us that this ancient light is more than a relic, it's a roadmap, guiding us deeper into the story of where we came from and how the universe grew from a seething fireball into the vast, structured expanse we call home. The cosmic microwave background isn't just light, it's a time capsule, a whisper from the universe's infancy that's been traveling for over 13 billion years. Imagine tuning an old radio between stations, hearing that static crackle. A tiny fraction of that noise isn't rand amidst the CMB, the faint afterglow of the Big Bang stretched into microwaves by the expansion of space itself. What makes this glow extraordinary isn't just its age, but its near-perfect uniformity. No matter where you point a telescope, the temperature hovers around 2.7 Kelvin, just a few degrees above absolute zero. That uniformity is cosmic inflation's calling card, evidence that the entire observable universe was once smaller than a proton, smoothed to homogeneity in those first explosive moments. But look closer and the CMB tells a richer story. Those tiny temperature variations, fluctuations no larger than 1 part in 100,000, are the universe's first brushstrokes. Slightly cooler patches correspond to regions where matter was denser, gravitational wells where galaxies would one day cluster. Warmer spots, those are the cosmic voids, stretched thin by the tug of surrounding structures. It's like examining the grain in a piece of wood. The patterns reveal the forces that shaped it. When scientists mapped these fluctuations with satellites like Planck and WMAP, they weren't just seeing noise. They were reading the blueprint for the cosmic web, the scaffolding of everything that exists today. The CMB does more than confirm the Big Bang. It's a window into the invisible. The way light from the CMB bends as it travels through space betrays the presence of dark matter, the mysterious substance that outweighs ordinary matter 5-1. Even dark energy, the enigmatic force accelerating the universe's expansion, leaves fingerprints in the CMB's large-scale patterns. These observations have led to a staggering conclusion. The stuff we can see, stars, galaxies, planets, makes up less than 5% of the universe. The rest is a cosmic mystery written in the subtle distortions of ancient light. Yet the CMB still guards secrets. Why do some large-scale features appear weaker than our models predict? Could there be hints of other universes in the polarization of these microwaves? Every new generation of telescopes peels back another layer, probing this primordial glow for answers. The CMB isn't just a relic, it's a conversation, a dialogue between the universe's first moments and our quest to understand them. And as we decode its whispers, we're not just learning about the past, we're glimpsing the fate of everything. While the cosmic microwave background reveals the early universe's blueprint, there's an invisible architect behind those patterns, dark matter. This mysterious substance, which neither emits nor absorbs light, was already weaving the cosmic web long before stars flickered to life. Think of it like a hidden scaffold, its gravity silently tugging at ordinary matter, guiding hydrogen atoms into the denser regions we see etched into the CMB. Without dark matter's relentless pull, those subtle fluctuations might never have grown into galaxies, or if they had, the process could have taken billions of years longer, leaving the universe a scattered, threadbare void. What makes dark matter so baffling isn't just its invisibility, it's how differently it behaves compared to everything we can see. Ordinary matter interacts through multiple forces. Electromagnetism binds atoms, the strong force glues nuclei, and collisions create friction and heat. Dark matter, though it's aloof, it feels gravity but ignores light and breezes past other particles like a ghost walking through walls. This indifference turned out to be cosmic luck. While normal matter was trapped in a tug-of-war with radiation constantly pushed apart by photons, dark matter's particles were free to clump together unimpeded, forming gravitational wells deep enough to eventually catch the swirling gas of the early universe. The evidence for dark matter's early influence is written in the CMB itself. The precise size and distribution of those temperature fluctuations match simulations only when dark matter is included, and not just a little, but 5 times more than ordinary matter. Some theories suggest dark matter might have even triggered the initial density variations during inflation, quantum ripples amplified into cosmic mountains by its invisible hand. Yet despite its obvious impact, we still don't know what dark matter actually is. Is it a sea of undiscovered particles like WIMP or actions? Could it be primordial black holes formed in the first seconds after the Big Bang? Or does gravity itself work differently on cosmic scales, rendering dark matter an illusion? Experiments deep underground and in space are hunting for answers, but the early universe offers its own clues. The way dwarf galaxies orbit larger ones, the lensing of distant starlight, even the speed at which galaxy clusters spin, all point to dark matter's scaffolding holding everything together. Its presence isn't just a modern mystery, it's the reason the universe looks the way it does. The atoms making up planets and people are mere afterthoughts, tracing patterns drawn by something we can't see. Dark matter didn't just shape the cosmos, it's the reason structure exists at all, a silent partner in the universe's grand design. And until we unravel its secrets, part of our origin story will remain hidden in the shadows. After eons of darkness, the universe finally flickered to life, not with the gentle glow of modern stars, but with a violent, brilliant blaze. These weren't just any stars, they were the first, forged from pure hydrogen and helium in the crucible of gravity's relentless pull. Picture a cosmic forge where gas clouds hundreds of times more massive than our Sun collapsed under their own weight, heating up until their cores ignited with a fury unmatched by anything in today's skies. These were population 3 stars, behemoths burning at temperatures over 100,000 degrees, their surfaces a searing blue-white, their lives measured in mere millions of years, a blink compared to our Sun's 10 billion-year lifespan. What made these stars so extraordinary wasn't just their size or heat, it was their purity. Born before heavier elements existed, they were pristine, uncontaminated by the ashes of earlier generations. This lack of metals, what astronomers call elements heavier than helium, changed everything. Without carbon or oxygen to help radiate away heat, these stars could grow monstrously large before fusion halted their collapse. Some may have reached masses 300 times that of our Sun, burning so fiercely they pushed the limits of physics itself. Their radiation didn't just illuminate the cosmos, it transformed it, flooding space with ultraviolet light so intense it ripped electrons from surrounding hydrogen atoms, reionizing the universe in a second great awakening. But these stars weren't destined to shine for long. Their very brilliance sealed their fate. Burning through their fuel at a breakneck pace, they died young in spectacular supernova explosions so powerful they briefly outshone entire galaxies. These violent deaths were cosmic alchemy in action, fusing hydrogen and helium into heavier elements like carbon, oxygen, and iron, then scattering them across the void. For the first time, the universe wasn't just hydrogen and helium. It was dusted with the seeds of future chemistry, the raw materials for planets, oceans, and life. Some of these stars may have even collapsed directly into black holes, their cores so dense not even light could escape, planting the seeds for the supermassive giants that would one day anchor galaxies. The legacy of population 3 stars isn't just written in starlight, it's etched into our very atoms. Every element in your body heavier than hydrogen traces its lineage back to these primordial furnaces. Their radiation sculpted the cosmic web, clearing the fog of neutral hydrogen and shaping the transparency of space itself. Yet for all their importance, we've never directly observed one. They live on only in simulations, and the chemical fingerprints they left in ancient gas clouds, ghosts of a time when the universe was young, hot, and unimaginably wild. Their story is a reminder that the cosmos didn't evolve gently. It was forged in fire, tempered by explosions, and shaped by stars that burned bright and fast, lighting the way for everything that followed. For hundreds of millions of years after recombination, the universe remained shrouded in darkness, not because light didn't exist, but because the vast sea of neutral hydrogen gas absorbed it like a cosmic sponge. Then something extraordinary happened. The first stars and galaxies flickered to life, their ultraviolet radiation piercing the fog like beacons in the night. This was reionization, the universe's great awakening, a slow-motion fireworks display where light fought its way through the cosmic murk, atom by atom, until the darkness finally lifted. The process wasn't gentle. Those early stars, especially the massive population Roman 3 giants, pumped out torrents of UV photons with enough energy to strip electrons from hydrogen atoms, tearing apart the very gas that had trapped light for so long. Imagine a wildfire spreading through a forest, only instead of flames, it was radiation wave after wave of energetic photons carving transparent bubbles in the hydrogen haze. Over time, these bubbles grew and merged, their edges overlapping like soap suds in a sink, until most of the universe's hydrogen was ionized once more. But this wasn't the same searing plasma of the Big Bang. It was a sparse, warm gas, thin enough for light to finally travel freely across cosmic distances. Quasars, the brilliant cores of distant galaxies powered by ravenous supermassive black holes, added fuel to the fire. As these black holes devoured surrounding gas, they unleashed jets of energy so intense they could ionize hydrogen far beyond their host galaxies. In some regions, quasars may have been the dominant force behind reionization, their radiation reaching places even the first stars couldn't illuminate. Together, stars and quasars waged a cosmic battle against the darkness, their combined efforts transforming the universe from opaque to transparent over hundreds of millions of years. The echoes of reionization linger in the most distant galaxies we observe. Their light, stretched by the expansion of space into infrared wavelengths, carries telltale signs of absorption by the last patches of neutral hydrogen like shadows cast on a fading curtain. By studying these ancient signals, astronomers have pieced together a timeline. Reionization likely began around 200 million years after the Big Bang and wasn't complete until nearly a billion years had passed. The universe didn't flip a switch. It dimmed the light slowly, unevenly, with some regions remaining stubbornly opaque long after others had cleared. This epoch wasn't just about visibility, it shaped the destiny of galaxies. The same radiation that ionized hydrogen also heated it, making it harder for gas to collapse into new stars. In a way, reionization put the brakes on star formation in the smallest galaxies, stunting their growth and leaving them as faint dwarf satellites orbiting larger neighbors. The universe's transparency came at a cost, but it also set the stage for everything we see today. Without reionization, the night sky would be a featureless void, our telescopes blind to the light of distant stars. The cosmic dark ages didn't just end, they gave way to a universe where light could finally tell its story. The first galaxies weren't the majestic spirals or glowing ellipticals we picture today. They were scrappy, chaotic things, barely holding themselves together in the turbulent early universe. Gravity had been patiently gathering hydrogen and helium around those subtle density variations from the cosmic microwave background, pulling matter into loose clusters where the first stars had already ignited. These protogalaxies were tiny by modern standards, maybe 1% the mass of our Milky Way, their shapes irregular and constantly shifting as new stars flared to life and died in spectacular supernova. What's remarkable is how quickly these fledgling structures appeared after the Big Bang. Within just a few 100 million years, a blink in cosmic time, the darkness was already giving way to islands of light. The James Webb Space Telescope has spotted some of these pioneer galaxies, their images stretched and reddened by 13 billion years of cosmic expansion. They're not the crisp, defined shapes we're used to seeing in nearby galaxies, but smudges of infrared light, their stars burning hot and fast in an environment far more extreme than anything today. Mergers were the driving force behind galactic evolution in these early epochs. Small protogalaxies collided frequently, their mutual gravity pulling them together into larger structures. Unlike the stately dances of modern galaxies, these ancient encounters were violent, chaotic affairs, a gas cloud smashing together, triggering furious bursts of star formation, while dark matter wove an invisible scaffold that held everything in place. Each merger built something bigger, paving the way for the diverse galaxy types we see today. The largest grew into the ancestors of modern galaxy clusters, while others remained small, becoming the dwarf galaxies that still orbit larger neighbors like the Milky Way. Studying these primordial galaxies is like finding the first few pages of a cosmic history book. Their chemical composition tells us about the stars that lived and died before them, the first heavy elements forged in those early supernovae. Their shapes reveal how gravity sculpted the universe when it was young, and their distribution mirrors the faint ripples in the cosmic microwave background, connecting the dots between the universe's smooth infancy and its structured present. Some even harbor supermassive black holes at their cores, puzzlingly large for such young galaxies, hinting at formation mechanisms we're still struggling to understand. These ancient starlight beacons are more than just relics. They're the foundation of everything we see today. Every galaxy, from the smallest dwarf to the largest cluster, traces its lineage back to those first, fragile assemblies of stars. And as telescopes peer deeper into the infrared sky, we're not just looking back in time, we're uncovering the blueprints of cosmic architecture, watching the universe learn how to build itself from the ground up. At the hearts of those early galaxies, something monstrous was stirring: supermassive black holes, cosmic leviathans weighing millions or even billions of times more than our Sun. These weren't just passive voids, they were engines of unimaginable power growing at rates that defy logic. The speed of their formation is one of the universe's greatest mysteries. If they started as ordinary stellar black holes, the remnants of dead stars, they'd need to consume impossible amounts of matter to reach such sizes in just a few 100 million years. Yet there they were, already fully grown when the universe was barely a toddler. One theory suggests these black holes skipped the stellar stage entirely, forming through direct collapse. Imagine a vast cloud of primordial gas, so dense and cold that it bypassed star formation altogether, collapsing directly into a black hole thousands of times the Sun's mass. These seeds would have had a head start, gorging on surrounding gas and merging with others to become the giants we observe. Another possibility involves chains of stellar collisions in tightly packed star clusters, where black holes could have merged repeatedly, snowballing into supermassive proportions. But neither explanation fully accounts for how these behemoths appeared so quickly, lighting up the young cosmos with their brilliance, and brilliant they were. As these black holes devoured gas and dust, the infalling matter didn't vanish quietly. It formed blazing disks of plasma, heated to millions of degrees and glowing brighter than entire galaxies. These were quasars, the universe's first lighthouses, their radiation so intense it could outshine 1,000 Milky Ways. Some quasars emitted jets of particles moving near light speed, carving through intergalactic space like cosmic blowtorches. Their light didn't just illuminate the early universe, it helped strip electrons from hydrogen atoms during reionization, contributing to the universe's transformation from opaque to transparent. But the most fascinating aspect of these black holes isn't just their size or luminosity, it's their intimate connection to galaxy formation. Far from being passive occupants, they actively shaped their galactic homes. The energy they released could heat surrounding gas, stifling star formation in some regions while triggering it in others. Their gravity dictated the motion of stars near galactic centers, and their mergers, when two supermassive black holes spiraled together, sent ripples through spacetime itself. The correlation between black hole mass and galaxy size is so precise that scientists now believe galaxies and their central black holes grew in lockstep, each regulating the other's growth through feedback mechanisms we're still unraveling. Yet questions remain. Why do some galaxies lack supermassive black holes entirely? How did the very largest, like the one powering the quasar-ton 618, a monster weighing 66 billion suns, form so early? The answers might lie in the chaotic environments of the young universe, where extreme conditions allowed for extreme objects. What's certain is that these black holes weren't just cosmic oddities, they were architects, their influence woven into the fabric of galaxies, including our own. The Milky Way's quiet central black hole, Sagittarius A star, is a sleeping giant compared to its ancient cousins, but its existence hints at a fiery past, a time when our galaxy too might have blazed with the light of a quasar, its heart a crucible of creation and destruction. The universe didn't just scatter galaxies randomly, it wove them into an intricate tapestry, a vast network of threads and voids stretching across billions of light years. This cosmic web, the largest structure we know, didn't emerge overnight. It grew from those faint ripples in the early universe, the ones imprinted in the cosmic microwave background, amplified over eons by gravity's patient pull. Picture a spider's silk spun across space, each strand a filament of dark matter and gas, studded with galaxies like dewdrops catching the dawn. Between these threads lie the voids, immense, nearly empty regions so large they could swallow thousands of Milky Ways whole. What's astonishing is how closely this web mirrors the universe's earliest moments. Those quantum fluctuations from inflation, microscopic jitters smaller than an atom, were stretched to cosmic proportions during the universe's rapid expansion. Gravity took these faint seeds and sculpted them, drawing matter into denser knots where galaxies would eventually bloom, while leaving other regions threadbare. The result is a pattern that repeats across scales, from the nearest galaxy clusters to the farthest quasars, a fractal fingerprint of the Big Bang itself. Modern simulations bring this process to life, tracing how dark matter's invisible scaffolding guided ordinary matter into place. Supercomputers running for months can recreate billions of years of cosmic evolution, their virtual universes sprouting filaments and voids that match sky surveys with eerie precision. These digital cosmos don't just confirm our theories, they reveal hidden details, like how galaxies prefer to align along filaments, their spins choreographed by the web's subtle tidal forces. Even the Milky Way sits on a filament's edge, part of the Laniakea supercluster, a single strand in the web's grand design, yet the cosmic web isn't static. It's a living structure reshaped by ongoing collisions and mergers. Galaxy clusters, the web's densest nodes, still grow by swallowing smaller neighbors, while dark energy's grip stretches the voids ever wider. Some filaments stretch so far they've been named the Hercules Corona Borealis Great Wall spans 10 billion light-years, a remnant of when the universe was half its current age. Peering into this web isn't just about mapping the present, it's a window into the forces that shaped everything. The way galaxies trace filaments hints at dark matter's role. The void's emptiness tests theories of cosmic acceleration. Even the web's faint glow, the warm gas between galaxies, carries echoes of the first star's explosive deaths. Every thread tells a story, connecting the quantum whispers of the Big Bang to the glittering cities of galaxies we see today. And as telescopes probe deeper, we're not just charting the web, we're learning to read it, deciphering how the universe turned chaos into order, one filament at a time. For most of cosmic history, gravity was the universe's great architect, pulling galaxies together, sculpting clusters, and slowing the expansion set in motion by the Big Bang. But around 5 billion years ago, something flipped. Instead of gradually slowing down, the cosmos began expanding faster, as if an invisible foot had pressed down on the accelerator. This mysterious force, dark energy, now makes up nearly 70% of the universe's total energy content, yet we have no idea what it actually is. The discovery of dark energy came as a shock. Astronomers studying distant supernovae in the late 1990s expected to find the universe's expansion decelerating under gravity's pull. Instead, they saw the opposite. The most remote explosions were dimmer than they should have been, meaning space had stretched more than predicted. The implication was staggering. Some unknown force was pushing galaxies apart with increasing speed. Further measurements from the cosmic microwave background to galaxy clustering confirmed it. Dark energy wasn't just real, it was winning its cosmic tug of war with gravity. What makes dark energy so baffling is how little we can say about it. The leading theory suggests it's the energy of empty space itself, what quantum physics calls vacuum energy. According to this idea, even a perfect vacuum isn't truly empty. It seethes with virtual particles flickering in and out of existence, generating a repulsive force that stretches space-time. The problem, when physicists calculate how strong this effect should be, their predictions overshoot observations by a factor of 10 to the power of 120. It's the worst mismatch between theory and experiment in all of science, a glaring sign we're missing something fundamental. Dark energy's fingerprints are everywhere. It explains why the universe is flatter than expected, why galaxy clusters stopped growing as rapidly, and why the cosmos will likely end in a big freeze, a gradual, icy dissipation as galaxies accelerate beyond each other's horizons. Yet its effects were negligible for most of cosmic history. In the early universe, matter and radiation were packed so densely that gravity dominated. Only when the cosmos became large and sparse did dark energy's subtle push overtake gravity's grip, like a steady breeze finally overcoming friction. Alternative theories abound. Some propose dark energy isn't constant but evolves over time, a field called quintessence that could weaken or strengthen. Others suggest Einstein's theory of gravity needs tweaking on cosmic scales. A few even speculate that dark energy hints at extra dimensions or a multiverse. But until we detect its nature directly, these ideas remain in the realm of speculation. One thing's certain: dark energy isn't just another cosmic ingredient, it's the scriptwriter of the universe's final act. If it continues unchecked, distant galaxies will vanish from view, their light stretched beyond detectability. The cosmos will grow cold and lonely, with only our local group of galaxies remaining gravitationally bound. Yet this mysterious force might also hold clues to physics beyond Einstein, a key to unlocking the deepest secrets of space and time. The universe's fate isn't written in the stars, it's hidden in the dark. The idea that our universe might be just one of many is both thrilling and humbling. Like discovering your hometown is a single grain of sand on an endless beach. This is the multiverse hypothesis, a radical extension of cosmic inflation theory, suggesting that the rapid expansion we think of as the Big Bang wasn't a one-time event. Instead, inflation could be eternal, continuously spawning new, bubble universes like froth in a never-ending cosmic simmer. Each of these bubbles would have its own unique physics, constants, and even dimensions. Some might have stronger gravity, others might lack electromagnetism entirely. In this scenario, our universe's finely tuned laws, the ones that allow stars and planets and life to exist, aren't special, just statistically inevitable in a sea of infinite possibilities. What's fascinating is how this idea emerges naturally from the math of inflation. When physicists trace the equations backward, they find that inflation doesn't have a clean stopping point. It could keep happening in some regions while ending in others, like a pot of water that never stops boiling. Regions where inflation ends become stable bubble universes, while the space between them continues expanding exponentially, forever pushing these cosmic islands apart. Some theories even suggest these bubbles could collide, leaving scars in the cosmic microwave background, though no definitive evidence has been found. The multiverse isn't just a wild guess, it solves real puzzles. For instance, why does our universe have such oddly specific constants? If gravity were slightly stronger, stars would burn out in millions of years instead of billions. If the cosmological constant were larger, galaxies could never have formed. In a multiverse, these values wouldn't need explaining, they'd just be the luck of the draw. one combination in an endless array of failed experiments. It's like tuning a radio. Most stations are static, but somewhere in the dial you'll find music. Critics argue this idea skirts the edge of science, since these other universes would be permanently beyond our observation. But supporters counter that the multiverse makes testable predictions, like certain patterns in the CMB or the energy levels of vacuum space. Even if we can't visit another bubble universe, its influence might still leave traces in our own. And if true, the implications are staggering, not just for cosmology, but for philosophy. The Big Bang wouldn't be the absolute beginning, just a local event in a much grander, possibly infinite metacosmos. Whether the multiverse is real or not, it challenges us to think bigger. Our universe might not be the grand stage of existence, just one act in an endless play, where the laws of physics themselves are as variable as the weather. It's a reminder that for all we've learned, the cosmos might still be hiding its greatest surprises beyond the horizon of our observable reality. To understand how the universe grew from a featureless fireball into the intricate cosmic web we see today, we have to zoom in, way in, to the realm of quantum mechanics. In the first moments after the Big Bang, space wasn't smooth and placid. It was a seething quantum foam, bubbling with fluctuations so tiny they'd make an atom look like a galaxy. Particles and energy flickered in and out of existence, borrowing energy from the vacuum itself in fleeting bursts allowed by the uncertainty principle. These weren't just random blips, they were the first brushstrokes on the canvas of the cosmos, the seeds from which all structure would grow. Inflation, that hyper-fast expansion of the early universe, took these quantum jitters and stretched them to cosmic proportions. Imagine blowing up a balloon with microscopic wrinkles on its surface. As it inflates, those tiny imperfections grow into vast mountains and valleys. That's exactly what happened to space itself. Regions that were slightly denser due to quantum fluctuations became the gravitational wells where matter would later accumulate, while less dense regions expanded into the voids we see between galaxies today. The fingerprints of this process are etched into the cosmic microwave background, where temperature variations of just 1 part in 100,000 reveal the universe's primordial unevenness. What's astonishing is how perfectly these quantum ripples match the large-scale structure we observe. Supercomputer simulations tracing the evolution of the universe from these initial conditions produce virtual cosmos that look eerily like our own, complete with filaments, clusters, and voids. Without these fluctuations, gravity would have had nothing to work with, no denser regions to amplify, no variations to sculpt. The universe would have remained a perfectly uniform sea of particles, cold and lifeless forever. The real magic lies in the connection between the unimaginably small and the incomprehensibly large. Quantum mechanics, which governs the behavior of particles on scales 1 billion times smaller than an atom, somehow set the blueprint for the distribution of galaxies across billions of light years. This bridge between quantum physics and cosmology is one of the most profound discoveries of modern science, revealing a hidden unity in nature's laws. It suggests that the universe's grandest structures, galaxies, superclusters, even the cosmic web itself, were born from the same rules that dictate how electrons orbit nuclei or photons behave as both particles and waves. Yet mysteries remain. Why did these quantum fluctuations have exactly the right amplitude to produce the universe we see? Some theories suggest inflation's energy field had just the right properties to amplify fluctuations to the observed level, while others propose deeper connections to quantum gravity or even the multiverse. Whatever the answer, one thing is clear: the universe's structure wasn't an accident. It was written into the fabric of reality from the very first moments, a delicate dance of chance and necessity that turned quantum whispers into the roar of galaxies. And in that dance, we find our own origins, every atom in our bodies, every star in the sky, tracing back to those infinitesimal ripples in the dawn of time. If you've ever walked into a room where the temperature feels perfectly even, no drafty corners or stuffy hotspots, you might not think twice about it. But imagine that room is the entire observable universe, stretching billions of light years in every direction, with regions so far apart that light from one side hasn't had time to reach the other since the Big Bang. Yet somehow those distant regions share nearly identical temperatures, matching to within a tiny fraction of a degree. This is the horizon problem, one of cosmology's most perplexing puzzles. How could parts of the universe that were never in contact with each other, never had time to exchange heat or information, end up so perfectly synchronized? The problem becomes even stranger when you consider the speed of light as the universe's ultimate speed limit. In the standard Big Bang model, without inflation, there simply wasn't enough time for distant regions to thermally equilibrate. It's like 2 cups of coffee placed on opposite sides of a football field, spontaneously cooling to the exact same temperature, despite never being connected. This shouldn't happen unless something in the early universe allowed these regions to communicate before they were flung apart. Inflation solves this riddle by rewinding the cosmic clock. Before the universe underwent its exponential expansion, all the matter and energy we see today was crammed into a volume smaller than a marble, a space so tiny that every part of it could easily reach thermal equilibrium. Then, in a fraction of a second, inflation stretched this uniform patch to cosmic proportions, carrying those once close regions far beyond each other's horizons. What we perceive today as distant, disconnected corners of the universe were once neighbors, sharing the same conditions before being separated by inflation's relentless push. The beauty of this solution is how well it aligns with observations. The cosmic microwave background, that faint glow from the early universe, shows temperature variations of just 1 part in 100,000, exactly the near-perfect uniformity inflation predicts. Without inflation, there's no obvious reason why the universe should be so smooth. With it, the horizon problem isn't just solved, it becomes a cornerstone of evidence supporting the entire theory. But inflation doesn't just explain uniformity, it also accounts for the tiny imperfections that seeded all cosmic structure. Those quantum fluctuations, stretched to astronomical scales during rapid expansion, became the density variations that gravity later sculpted into galaxies. The same mechanism that smoothed the universe also planted the seeds for its complexity. It's a delicate balance, one that suggests the early universe wasn't just a random fireball, but a system with precisely tuned dynamics. Critics have proposed alternatives, ideas like variable speed of light or bouncing cosmologies, but none match inflation's explanatory power or fit the data as neatly. The horizon problem wasn't just a minor curiosity. It was a glaring flaw in the classical Big Bang model, one that pushed theorists to imagine something as radical as inflation. And in doing so, they didn't just patch a hole, they uncovered a deeper layer of cosmic history, revealing how the universe's largest structures trace back to its smallest moments. The horizon problem reminds us that sometimes the most profound insights come from asking why things seem too perfect to be accidental. Imagine balancing a pencil perfectly on its tip so precisely that even after billions of years, it hasn't fallen over. That's essentially what the universe has done with its geometry. Measurements from the cosmic microwave background reveal something astonishing. Space-time is flat too, within a margin of error of just 1%. Not positively curved like a sphere, not negatively curved like a saddle, but perfectly, inexplicably flat. This isn't just a curious observation. It's a cosmic tightrope act that defies logic without inflation. The flatness problem starts with Einstein's revelation that matter and energy curve space-time. The more stuff you pack into the universe, the more it bends, like placing weights on a rubber sheet. But here's the catch: for space to appear flat today, the early universe's density had to be fine-tuned to an absurd degree, within 1 part in 10 to the power of 60 of the critical density. That's like adjusting the entire cosmos's energy budget to the precision of a single atom in a galaxy. Without some mechanism to enforce this balance, even the tiniest deviation in the first second would have snowballed over billions of years into a universe either collapsing into a big crunch or tearing itself apart in runaway expansion. Inflation solves this with a cosmic sleight of hand. By stretching space exponentially in the first fraction of a second, it smoothed out any initial curvature like flattening wrinkles on a balloon as it inflates. Picture drawing a small triangle on a deflated balloon. Its angles might add up to more or less than 180 degrees depending on the balloon's curvature. But blow it up to the size of a house, and those angles approach perfect Euclidean geometry. Inflation did the same to the universe, magnifying an initially tiny patch so vastly that any primordial curvature became undetectable. What's elegant about this solution is how it ties into other cosmic mysteries. The same runaway expansion that flattened space also stretched quantum fluctuations into galaxy-forming seeds and ironed out temperature differences across the horizon. Inflation doesn't just explain flatness, it turns a fine-tuning problem into a natural outcome. The universe isn't flat because of some improbable coincidence. It's flat because inflation erased the memory of its initial shape, leaving behind the featureless geometry we measure today. Yet this raises deeper questions. If inflation can produce a flat universe so effortlessly, could there be other regions beyond our observable horizon with different geometries, bubbles of positive or negative curvature? Some multiverse theories suggest exactly that, painting our flat expanse as just one possibility in a grander cosmic landscape. The flatness problem isn't just about geometry. It's a window into the universe's most fundamental workings, showing how the largest-scale properties of reality might be written in the language of quantum fields and exponential expansion. And that perfect pencil balance, it's not luck, it's the signature of a process so powerful it turned chaos into precision on a cosmic scale. One of the most profound puzzles in cosmology isn't just how matter came to exist, but why it exists at all. According to everything we know, the Big Bang should have created equal amounts of matter and antimatter, particles, and their mirror image counterparts with opposite charges. When these opposites meet, they annihilate in bursts of pure energy, leaving nothing behind. So why does our universe contain galaxies, stars, and planets instead of an empty sea of radiation? The answer lies in an almost imperceptible flaw in nature's symmetry, a tiny preference for matter over antimatter that emerged in the universe's first microseconds. This imbalance, called Baryon asymmetry, is like finding a single grain of sand surviving on a scale that should be perfectly balanced. For every billion matter-antimatter annihilations in the early universe, roughly one matter particle avoided destruction. That razor-thin margin, just one extra particle in a billion, was enough to seed everything we see today. The rest vanished in a blaze of gamma rays, their energy now diluted into the cosmic microwave background. But what caused this critical asymmetry? The leading suspect is a phenomenon known as CP violation, where particles and their antimatter counterparts behave slightly differently under certain conditions. The first evidence for CP violation came from studying subatomic particles called kaons in the 1960s, and later with beauty quarks at particle accelerators. These experiments revealed that antimatter particles don't always mirror their matter twins perfectly. They decay at subtly different rates, like two supposedly identical clocks ticking out of sync. In the extreme conditions of the quark epoch, this microscopic bias could have tilted the scales, allowing a slight excess of quarks to survive annihilation. But here's the catch. The amount of CP violation we've measured so far isn't nearly enough to explain the matter dominance we observe. There must be other, undiscovered sources of asymmetry lurking in nature's laws. This mystery has sent physicists hunting for clues in some of the most extreme environments imaginable. The Large Hadron Collider smashes particles together at energies not seen since the universe's first moments, searching for new forms of CP violation. Underground detectors monitor the decay of neutrinos, ghostly particles that might behave differently from their antimatter counterparts. Some theories even suggest that the imbalance originated before the quark epoch, during an era when hypothetical heavy particles decayed unevenly, favoring matter. Others propose that antimatter galaxies might exist in distant regions of the cosmos, separated from us by vast stretches of empty space. The implications of Baryon asymmetry stretch far beyond particle physics. Without this 1 in a billion surplus, stars wouldn't shine, planets wouldn't form, and life would never have arisen. It's a reminder that the universe's most pivotal moments often hinge on the smallest details, a fractional difference in particle behavior that echoed across billions of years. Solving this mystery wouldn't just explain why we're here, it could reveal entirely new laws of physics hidden in the subtle cracks of nature's symmetries. And every experiment brings us closer to understanding how a universe that began with perfect balance ended up tipping ever so slightly, just enough to create everything. Hidden in the faint whisper of the cosmic microwave background may lie the faintest tremors of the universe's birth, gravitational waves from the first trillionth of a second after the Big Bang. These aren't the gravitational waves we've detected from colliding black holes or neutron stars. These are primordial, stretching back to the inflationary epoch itself, when space expanded faster than light could chase it. According to theory, inflation's violent stretching of spacetime should have sent shockwaves rippling through the very fabric of reality, leaving behind a distinctive curl in the polarization patterns of the CMB, a cosmic fingerprint waiting to be decoded. Finding these waves would be like uncovering a recording of the universe's first cry. Unlike light, which scatters off particles, gravitational waves travel virtually unimpeded, carrying pristine information about the conditions that created them. The energy scale of inflation was so extreme, trillions of times hotter than the core of the Sun, that no particle accelerator on Earth could ever recreate it. But these waves, they're messengers from that unreachable frontier, encoding details about the inflationary field's strength, how quickly it decayed, and even potential clues about quantum gravity. The hunt for these signals has led scientists to some of the most inhospitable places on Earth, like the South Pole, where the BICEP and Keck array telescopes scan the sky through the clearest, driest air on the planet. These experiments don't look for light or heat. They search for a subtle twisting in the CMB's polarization called B modes, the telltale swirls left behind by gravitational waves. In 2014, the BICEP team thought they'd found it, but the signal turned out to be cosmic dust in our own galaxy. The lesson was clear. Separating inflation's whisper from the universe's background noise is like listening for a single violin in a symphony orchestra. Future missions, like the proposed Lightbird satellite or next-generation ground-based observatories, aim to cut through the noise with unprecedented sensitivity. Some theories suggest these waves could be strong enough to detect within a decade. Others warn they might be too faint for any foreseeable technology. But the stakes couldn't be higher. A detection wouldn't just confirm inflation, it would tell us which version of inflation happened, ruling out entire classes of theories. Some models predict a loud, unmistakable signal, others a near-silent hum. The volume of these waves would reveal the energy scale of inflation itself, letting us peer directly into an era when all the forces of nature were still unified. And if we find nothing, that would be just as revolutionary. It might mean inflation happened at lower energies than expected, or that our understanding of the early universe needs a radical rewrite. Alternative theories like bouncing cosmologies or string gas scenarios could gain traction. Either way, the search for primordial gravitational waves isn't just about validating the past, it's about narrowing down the future of physics itself. These elusive ripples aren't just echoes, they're a bridge between the quantum realm and the cosmos, a chance to witness the moment when the universe decided what it would become. The faint glow of the cosmic microwave background isn't just a uniform blanket of radiation. It's a patchwork quilt of subtle temperature differences, a tapestry of hot and cold spots that tell the story of the universe's infancy. These anisotropies, variations as small as 1 part in 100,000, are like cosmic hieroglyphics encoding secrets about the universe's composition, shape, and even the weight of ghostly neutrinos. When satellites like Planck and WMAP mapped these fluctuations with razor-sharp precision, they weren't just taking a snapshot, they were decoding the universe's genetic blueprint. Each of those temperature variations corresponds to a slight over or under density in the early universe, regions where matter was ever so slightly more or less concentrated. The hotter spots mark where gravity would later pull gas and dark matter into galaxies and clusters, while the cooler patches became the vast voids separating them. It's astonishing to think that the sprawling cosmic web with its filaments of galaxies stretching across billions of light years traces back to these microscopic ripples, stretched to cosmic proportions during inflation. The pattern isn't random either. The distribution of these fluctuations follows a precise mathematical rhythm, like notes in a cosmic symphony, revealing the exact moment when sound waves raced through the primordial plasma. But the CMB's anisotropies don't just map structure, they are also a forensic tool for weighing the universe's ingredients. The way those temperature variations are distributed tells us that ordinary atoms make up less than 5% of the cosmos, while dark matter accounts for about 27%. The rest, dark energy, that mysterious force accelerating the universe's expansion. Even neutrinos, the lightest and most elusive known particles, leave a signature. Their tiny mass subtly alters how those early density variations evolved, leaving a faint smearing effect in the CMB's small-scale patterns. Perhaps most remarkably, these anisotropies act as a cosmic ruler. The apparent size of the temperature fluctuations on the sky depends on the universe's geometry, whether space is flat, positively curved like a sphere, or negatively curved like a saddle. The measurements leave no room for doubt. Space is flat to within a fraction of a percent, just as inflation predicts. The CMB doesn't just show us the universe's baby pictures, it hands us the owner's manual, complete with specs on its shape, contents, and even its age. Yet for all we've learned, the CMB still holds mysteries. Some large-scale patterns don't quite match predictions, like a curious cold spot spanning multiple degrees of sky. Could these be statistical flukes or hints of exotic physics? Others have scoured the data for signs of primordial gravitational waves, the smoking gun of inflation, though definitive proof remains elusive. Every new generation of telescopes peels back another layer, probing finer details, hunting for polarization patterns that could reveal even earlier epochs. The anisotropies aren't just relics, they're a living record, a Rosetta Stone for the cosmos, waiting for us to decipher its next chapter. Of all the particles streaming through the cosmos, neutrinos might be the most enigmatic ghosts of the subatomic world, slipping through planets and people alike with barely a whisper of interaction. Born in the furnace of the early universe, these nearly massless particles outnumber atoms by billions to one, yet their presence is so subtle you'd never know they were there. Every second, trillions of neutrinos from the sun and distant cosmic events pass through your body, leaving no trace. But in the first seconds after the Big Bang, these elusive particles weren't just bystanders. They were cosmic sculptors, their gravity subtly shaping the universe's infancy in ways we're only beginning to understand. What makes neutrinos so fascinating is how they defy expectations. Unlike electrons or quarks, they barely interact with matter at all. A neutrino could travel through a light year of lead without slowing down. Yet despite their ethereal nature, they carry mass, a revelation that earned the Nobel Prize in Physics in 2015. This tiny weight, millions of times lighter than an electron, might seem insignificant, but in the early universe's dense soup of particles, it was enough to leave fingerprints on everything. As neutrinos zipped around at near light speed, their gravity tugged ever so slightly on the primordial plasma, smoothing out some density fluctuations while amplifying others. The result, a faint but detectable pattern in the cosmic microwave background, and the large-scale distribution of galaxies, a shadow of their influence frozen in time. The holy grail of neutrino cosmology would be detecting the cosmic neutrino background, the relic neutrinos from the Big Bang itself. While the cosmic microwave background captures the universe at 380,000 years old, these neutrinos decoupled from matter just 1 second after creation, carrying a snapshot of the cosmos in its fiery infancy. Catching them would be like finding a recording of the universe's first breath. The challenge: these neutrinos have cooled to just 2 degrees above absolute zero, their energy so low that even state-of-the-art detectors struggle to pick them out from the noise. Some proposals suggest using arrays of ultra-pure crystals or massive tanks of liquid argon, waiting for the once-in-a-lifetime collision where a relic neutrino finally makes its presence known. Beyond their role as cosmic witnesses, neutrinos might hold clues to even deeper mysteries. Their tiny masses could hint at undiscovered physics beyond the standard model, perhaps tied to grand unification or even the origins of matter-antimatter asymmetry. Some theories suggest that sterile neutrinos' hypothetical, even more elusive cousins could be dark matter candidates, weaving the invisible scaffolding of the cosmos. Others propose that neutrino oscillations, where these particles morph between different types mid-flight, might reveal hidden dimensions or new symmetries of nature. What's certain is that neutrinos are more than just cosmic afterthoughts. They're living fossils from the universe's first moments, silent travelers carrying secrets across billions of years. Every time we detect one, whether from the sun, a supernova, or someday, the Big Bang itself, we're tapping into a conversation that began when time itself was young. And in their quiet persistence, they remind us that the universe's grandest stories are often written in the faintest ink. The Big Bang isn't the only story science has tried to tell about the universe's origins, just the one that survived the harshest test. Among its earliest challengers was the steady-state theory, a mid-20th century proposal that painted the cosmos as eternal and unchanging. Picture an infinite universe where new matter continuously forms to fill the gaps as galaxies drift apart, maintaining perfect cosmic equilibrium. No explosive beginning, no dramatic evolution, just an endless, self-renewing dance. For a time, this elegant idea held real sway, appealing to those uncomfortable with the notion of a definitive starting point. But the cracks began showing when astronomers discovered quasars' distant, hyperactive galactic cores that looked nothing like their modern counterparts. These cosmic lighthouses revealed a universe that had changed dramatically over time, their very existence contradicting steady-state's core premise. The final blow came with the cosmic microwave background's detection, that unmistakable afterglow of a hotter, denser past. Yet even as steady state faded, other alternatives emerged to tackle lingering questions about the Big Bang's rougher edges. Take bouncing cosmology, which replaces the singularity, that infinitely dense starting point where physics breaks down, with a cosmic rebound. In this scenario, our expanding universe was born from the collapse of a previous one, like a phoenix rising from gravitational ashes. The math suggests that under certain quantum gravity models, a contracting universe wouldn't crush itself into oblivion, but would instead reach a minimum size before springing back outward. This elegant sidestep not only avoids the singularity's paradoxes, but hints at an infinite cycle of universes, each inheriting subtle traces from the one before. Then there's the plasma universe hypothesis, which swaps gravity's dominance for electromagnetism's power. Proponents point to the filamentary structures seen in galaxy clusters, patterns that mirror laboratory plasma behaviors, as evidence that cosmic-scale electric currents might shape the universe more than we realize. Others explore variable speed of light theories, where light traveled faster in the early universe, potentially explaining how distant regions reached thermal equilibrium without inflation. What keeps these ideas alive isn't just contrarian spirit, it's the healthy skepticism that drives science forward. Every time an alternative theory forces researchers to recheck their assumptions, our understanding deepens. The Big Bang model itself evolved through such challenges, incorporating inflation to solve horizon and flatness problems that earlier versions couldn't explain. Today's leading theory may someday face its own reckoning, refined or replaced by ideas we've yet to imagine. The beauty of cosmology lies in this tension between evidence and imagination. While most alternatives falter when confronted with observations like the CMB's precise fluctuation patterns or the universe's elemental recipe, they push mainstream science to articulate its case more clearly. Like detectives comparing competing theories, physicists weigh each proposal against the full forensic record. The light of distant supernova, the whispers of gravitational waves, the intricate web of galaxies. In the end, the universe gets the final say, revealing its history not through human preference, but through the unflinching language of data. And that's how the grandest story ever told keeps rewriting itself, one bold idea, one rigorous test at a time. The next chapter in our cosmic origin story won't be written in textbooks. It'll be etched into petabytes of data from telescopes so advanced they border on science fiction. Imagine instruments sensitive enough to detect the faint twist in ancient light patterns left by gravitational waves from the universe's first trillionth of a second. That's the precision we're now chasing with projects like the LightBird satellite, slated to launch in the late 2020s with detectors chilled to near absolute zero, scanning the cosmic microwave background for the distinctive swirls called B modes. These elusive patterns could finally prove whether inflation happened at the energy scales predicted by grand unified theories, or if we've been missing something fundamental all along. On the ground, arrays like the Simons Observatory in Chile's Atacama Desert are taking complementary approaches, deploying thousands of superconducting detectors to map the CMB's polarization across 40% of the sky. What makes these efforts revolutionary isn't just their sensitivity, it's how they'll cross-examine inflation's many competing models. Some versions predict a loud, unmistakable gravitational wave signature, others, a whisper barely distinguishable from cosmic dust. The absence of a signal might be just as revealing, forcing theorists back to the drawing board to explain how quantum fluctuations became galactic seeds without inflation's exponential stretch. Meanwhile, the James Webb Space Telescope is rewriting the timeline of cosmic dawn, discovering galaxies so massive and mature in the universe's first few 100 million years that they challenge our understanding of structure formation. Could these be the products of rare density peaks amplified by exotic inflation fields, or do they hint at alternative scenarios where early black holes jump-started galactic growth? Upcoming 30-meter class telescopes like the UNTOLD will scrutinize these pioneers in unprecedented detail, analyzing their chemical compositions for clues about even earlier epochs. Equally transformative are dark energy surveys like DAISY and Euclid, mapping millions of galaxies to reconstruct how inflation's initial density variations evolved into today's cosmic web. By tracing the distribution of matter across billions of light years, these projects test whether dark energy's acceleration aligns with inflation's flat universe prediction, or if subtle spatial curvatures emerge at scales beyond previous measurements. Some theories suggest inflation's imprint might hide in the statistical clustering of distant quasars, while others propose hunting for concentric ring patterns in galaxy distributions, potential evidence of pre-Big Bang bubble collisions in the multiverse. The most radical experiments venture beyond photons altogether. Pulsar timing arrays harness the cosmic metronomes of spinning neutron stars to catch low-frequency gravitational waves from supermassive black hole mergers, and potentially from cosmic strings left over from symmetry breaking after inflation. Future space-based detectors like LISA could extend this hunt to frequencies where primordial waves from inflation's final moments might resonate. Even particle colliders play a role, with the high-luminosity LHC searching for supersymmetric particles that could have influenced inflation's energy landscape. What unites these diverse approaches is their potential to transform abstract cosmology into observational fact. The coming decade could either cement inflation's status as the cornerstone of modern cosmology or force a paradigm shift as dramatic as the Copernican revolution. Either outcome would mark a triumph not just for our understanding of the universe's birth, but for humanity's relentless curiosity to decode existence itself. The tools are being forged, the data pipelines primed. We stand on the threshold of revelations that could rewrite our cosmic origin story in ways no one yet anticipates. The discovery that our universe had a beginning, a definitive moment where time, space, and matter burst into existence, doesn't just rewrite science textbooks. It reshapes how we understand reality itself. Before the Big Bang theory took hold, many assumed the cosmos was eternal and unchanging, a static stage where the drama of stars and galaxies played out on an infinite timeline. But the realization that everything we know emerged from a searing, dense origin flips that script entirely. Suddenly, we're not passive observers in an everlasting universe. We're participants in a grand, evolving story with a starting point and potentially an end point. This awareness does something profound. It turns cosmology from a niche science into a mirror, reflecting our deepest questions about meaning, purpose, and our own fleeting presence in the cosmic expanse. Consider what it means that the universe evolves. Every galaxy, every star, every atom in your body exists because conditions 13.8 billion years ago were precisely tuned to allow complexity to emerge. If the strength of gravity or the nuclear forces had been even slightly different, atoms might never have formed, and the cosmos would be a featureless void. This fine-tuning isn't just a scientific curiosity. It's a puzzle that bridges physics and philosophy. Does the universe's apparent perfection suggest a deeper principle we haven't uncovered yet? Or does it point to the existence of a multiverse, where countless other universes with different laws flicker in and out of existence beyond our view. The Big Bang doesn't just give us answers, it opens doors to mysteries we're only beginning to articulate. Then there's the humbling scale of it all. The observable universe spans 93 billion light-years, a staggering volume filled with 2 trillion galaxies. Yet all that grandeur traces back to a single, unimaginably hot and dense point. There's something poetic in that, a reminder that the vast and the infinitesimal are intimately linked. The quantum fluctuations of the early universe became the galaxies we see today. The same laws governing subatomic particles dictate the motion of galaxy clusters. This unity suggests an underlying order, a mathematical elegance that makes the cosmos comprehensible to human minds. The fact that we can trace the history of the universe back to its first moments, using nothing but observation and reason, is a testament to the power of science and to the universe's willingness to reveal its secrets. But perhaps the most profound implication is existential. If the universe had a beginning, could it also have an end? Will it expand forever into cold darkness or collapse back into a fiery crunch? These aren't just technical questions, they shape how we think about time, legacy, and the significance of life in an impermanent cosmos. The Big Bang tells us we're not separate from the universe, we're its product, forged in stars and shaped by billions of years of evolution. Every breath you take contains atoms created in the hearts of supernova, linking you directly to the universe's violent, creative past. That connection transforms astronomy from a distant science into a personal journey, a way to understand not just where we came from, but what we might become. In the end, the Big Bang is more than a theory, it's a foundation for wonder. It invites us to look up at the night sky not with passive awe, but with active curiosity, knowing that the light reaching our eyes carries stories from the dawn of time. It challenges us to keep asking questions, to push beyond the edges of our understanding, and to embrace the beautiful truth that the universe is not just stranger than we imagine, but stranger than we can imagine. And in that endless mystery lies its greatest gift, the reminder that we're part of something far grander than ourselves, a cosmic drama still unfolding with countless chapters yet to be written.